Alright, so valence electrons are considered to be the outermost electrons in an element's configuration, in an atom's structure. And the reason they're so important is because the valence electrons determine how an element is going to behave. So let's just take a look first at the pattern. Every element in column 1 or group 1, the alkali metals, has a valence of 1. Column 2, alkaline earth metals, a valence of 2. So very easy to see. The transition metals, which basically go from column 3 to column 12, aren't as easy to predict. They don't follow a nice set pattern, so we really don't use the transition metals when we're predicting valence. They have valence values, it's just they're not as easy to predict as other elements. So we jump to group 13, and valence is never going to be higher than 8. So it doesn't match, since say group 13 has a valence of 13. It's actually the second, the digit in blue matches the valence. So column 13, valence of 3, column 14, 4, 15, 5, 16, 6, 17, 7. And the last group, noble gases, valence of 8, with helium being the exception. It only has a valence of 2. Most elements follow what's called the octet rule. Basically what that means is they want to have a valence of 8. 8 is considered their goal. So if they don't have a valence of 8, they react with other elements to achieve a valence of 8. It's called the octet rule. There are some elements that follow what's called the duet rule, and that's basically the elements you see listed, those 5 there, but there aren't many elements that follow the duet rule. So most elements follow the octet rule. So 8 is the magic number. When an element achieves stability, that means that they've achieved a valence of 8. So how are they going to do this? Well, they can do it by losing electrons, gaining electrons, or sharing electrons. And they're going to lose or gain the electrons according to their valence. So if you have a valence of 3 or less, you're going to lose electrons. If you have a valence of 5 or more, you're going to gain, and then we'll talk about valence of 4 later. Most metals have low valence values, 3 or lower, so they tend to lose electrons. Most nonmetals have valences of 5 or higher, so they tend to gain electrons. You could look at it as elements are lazy, meaning they're going to do what's easier. So if I have a valence of 3, I could lose 3 or gain 5. I'm going to do what's more cost effective. I'm going to lose 3. Or if you have a valence of 5, I could gain 3 or lose 5. Well, gaining 3 is more cost effective than losing 5. So it depends on their valence whether they're going to gain or lose electrons. So if you have a valence of 1, you want to lose that 1 electron and drop down to the next full shell. If you have a valence of 2, you're going to want to lose 2. Valence of 3 is going to lose 3. Valence of 5, remember the magic number is 8. So if you have 5, you want to gain 3 to make that total 8. If you have a valence of 6, you want to gain 2 to make the total 8. And if you have a valence of 7, you want to gain 1 to make that total 8. It's harder to see with the elements that lose electrons, but when you look at the electron configuration, you'll see what I mean. Now, gaining or losing with electrons that have a valence of 4 just depends on the conditions that the elements are reacting. Sometimes they could share electrons, depending on the pressure involved, the temperature, what the elements are reacting. It's very hard to predict. So valence of 4, they could gain, lose 4, or they could also share electrons. So why do these elements want 8? Well, because all noble gases, with the exception of helium, have this valence of 8. And as we know, noble gases are stable. They don't react. So you can look at it as elements wanting to be like the noble gases. Think of the noble gases as kind of like a they want to be a role model for the rest of the elements. Noble gases are kind of like the role models for the other elements. They all want to achieve this, this valence of 8. In other words, they want to achieve configuration. So if you look at argon, 1s2, 2s2, 2p6, 3s2, 3p6, and then you look at chlorine, you'll notice that they are 1 off. And that means, we already know that chlorine has a valence of 7 because it's in column 17. And if you don't see that, let's take a look here. Remember that the coefficients represent the outermost energy level. And what is valence? Valence is the electrons in the outermost energy level. So there's 2 here in the S sublevel, and there's 5 here in the P. Well, 2 plus 5, that's a valence of 7. So what does chlorine want to do? Well, it wants to gain 1 electron. And if it gains 1 electron, it will look just like argon's configuration, because it wants to look like its nearest noble gas. So chlorine is going to gain that 1 electron, but it has to give up its identity and become a compound for that to happen. Well, let's take a look at neon. Neon's 1s2, 2s2, 2p6, and let's look at sodium. Sodium ends in 3s1. Now, what could sodium do? Well, sodium could gain 7 and look like argon, 3s2, 3p6, and have a valence of 8, or it could lose this 1 electron here. And when it does that, what is its configuration going to look like? Well, it's going to look like neons. Because now that this outermost electron is gone, these become the outermost electrons. 2 plus 6 gives you that 8. So this is why sodium wants to lose that electron, because it wants to become like neon. So if sodium wants to lose 1 and chlorine wants to gain 1, when they react, the formula that they end up with is a 1-to-1 ratio. It's what we call a perfect fit. So this is a way that you can help predict how elements are going to behave by their valences. You can tell if what their ratio is going to be when they react. All right, so that's part 8, and we'll continue with part 9.